Nobody's here. Martin sent a link, but it seems like it's not here. Because I can't see him.
All right. Good morning, guys. Hello.
Okay. Hello?
Hello, good morning.
Hello, good evening. We are here in Chiba, Japan.
Okay. Good morning. There we go. How are you guys doing?
We are doing fine.
Cool. Excellent. So I'm still waiting for some more people here. You guys ready in 15 minutes?
Yeah, but we just want to make sure that we test the connections before we start the job.
Do you want to test the screen sharing?
Yes, and the microphone. Can you hear me clearly?
Yeah, it's fine. It's fine. Yeah.
Oh, okay, okay. Then,
so if you want to try to share your screen,
let's do the screen share.
Report slide.
Can you see my desktop?
Yeah, I can see your desktop.
Oh, okay.
I can see. Yeah,
can you see the presentation?
Yeah, looks perfect. Very nice. Yeah. Yeah, excellent. Okay, I think that works fine.
Oh, okay. So I should come back maybe 10 minutes before the time?
Yeah, that sounds good. 5-10 minutes before.
Oh, okay. Thank you.
All right. See you later.
Yeah, the option. That's for my software.
Sorry, just one.
Yeah, but there are 3 parts. All 3.
Oh, yes. Thank you.
Combined.
Good morning.
Good morning.
The government project. What?
Jose Carlos.
Good morning, Martin.
Good morning. How
Are
are
you
you?
okay?
Yeah. Here we are getting ready. It's early, but good.
Oh, that's for the first team.
Yeah, they're coming up now.
Are they from Plymouth or not?
There's a mix. We have 3 from Chiba and 3 from Plymouth.
I have to look for this course sheet.
There.
Morning, Tapio. Can you hear me?
Yeah, I can hear you.
Okay.
But we are in the same room with Norman
Sorry?
and Wolf, so it might be circling.
There's a bit of feedback
Might
in
be
your
circling
line.
here.
Okay. Okay, so for the presentation, Norman, do you guys in Chiba want to start off presenting for about 7-8 minutes, and then the people in Plymouth take over?
Yes, we will be happy to start.
Okay, perfect. So we'll give everyone about 5 more minutes to make it, and then we'll start off.
No problem.
Yeah, everything you do.
Hmm?
The mic is open.
The mic is open. Our mic is open.
Yes.
Is it working?
Yeah, I think so.
Okay, okay.
But remember to mute your microphone. Talking.
When we are not talking, we must mute the microphone.
With no announce
From.
session. The upper part.
But now I'm seeing only this this screen.
No. It's in the Hangouts.
Because if it's this, then I need to go back to Hangouts and then this one.
Okay, so it's 5 past. I think we should get started. So welcome everybody to this last day of the student presentations for 2015 ShanghAI Lectures. We have a nice program today. We have 3 groups coming up, most of them dealing with kind of soft robots. It should be interesting. We'll start off now with group 1, which is a mix of groups from Chiba and from Plymouth. So I think the guys in Chiba will start off. So guys, whenever you're ready, feel free to start your presentation.
Thank you. I think we are ready. Can we start?
Okay, yeah, go ahead.
Okay, thank you. We are from Chiba. This is Norman who will be presenting on behalf of the team. With me, Jiang Wu, but one of our students has traveled to China for some academic reasons, so we won't be able to be with him now. So the content of our presentation will be introductions, the materials we used, and some methods, some results that will demonstrate, conclusions, and some future works. So generally, we find juggling the balls being an easy task to human beings. They can demonstrate their skills by juggling 2 or 3 balls, but unfortunately, human beings cannot succeed in juggling balls without a lot of practice. And currently, we have also discovered that juggling balls is a difficult task for ordinary robots. But now, with some progress in technology and machine learning algorithms, we can see robots learning to juggle 2 ping-pong balls at 120 Hz. But sometimes you find it struggling to learn to juggle the 2 balls. But at least we can demonstrate some success that robots can learn to juggle the balls also, with some specialized end effectors in order to execute such tasks. But now, what if we increase the number of balls from 5 maybe to 3, 4, or 5? We can see that 5 balls juggling is the most difficult. You can't?
Yeah, the video is killing the wonderful.
Oh, okay.
And mute the video.
Okay. So when you increase the number of balls, then you increase the complexity of juggling. So you find it very difficult to control all the 5 axes because they need to be controlled synchronously. And throwing the 3rd ball, the 4th ball, the 5th ball, they all require splitting the juggling kinematics. And all these kinematics should be controlled in the right time and in the right order. You don't just control them. But at least with a high-speed camera system, you can control all these kinematics equations of motions. So in our case, we are using the stereo vision system with 2 cameras and the LED light source, and we also have the high-speed head arm and the toss machine which toss the balls. So the high-speed hand, it has 3 fingers with some soft sponge across the fingers. So it's a kind of a soft robotic hand. And the maximum speed for these fingers is about 4.5 seconds. And the maximum power for grasping of all these fingers is about 28.5 newtons. And it has 3 fingers, and they all in total have 8 degrees of freedom. And the weight of each finger is about 450 grams. And from each, we have both thumb having the pivot joints with various configurations. And the tossing machine, you can see, is concealed by a black cover. There is a black bag there covering the machine so that it cannot be seen from the camera. So the camera should only detect the ball when the toss machine is tossing the balls. And we are using 2 polyethylene foam balls of about 19 grams. And the high-speed vision system uses the IDP Express from Hiroshima. And this machine uses the IDP Express board, which is connecting to the visual system, and we connect that to the PC. And the Ethernet is used to connect all the systems so that they can work together and synchronously and being coordinated together. Because we are using the visual system, we decided to use the stereo vision system to get the 2 outputs from each camera into a combined visual system which will produce 1 image. And after getting that image, we do the background subtraction, we extract the color and binarize it. And then we set the region of interest, of which in this case is the ball that we are looking at. And then from that we calculate the image moment, we correct the distortions from the visual system, which is our stereo vision in this case. And for each ball, we can get its center of mass in pixel coordinates at about 500 Hertz. And all this image processing, they are being processed using CUDA for speed. And basically, this is the flowchart, which is for image processing. You get the position of the ball, extract. If we we are finding so many areas in the image, then we get the region of interest that we get in the ball. And then we get the background, differencing, extract the color, bannerize the image, and then we calculate the ideal center of mass of each ball. So basically, this is the same thing. Now, when we are processing the juggling motion, we need to look at the original state of the hand, and we also consider the motion of the ball. And we also consider the target ball and its moving, where we get its speed, and then we need to follow it through. And when we are pursuing its trajectory, we need to determine whether the hand will be able to reach at that space. So in this case, we need to calculate the reachable region of the hand. And if we find that the hand cannot reach the position of the ball, we just stop the motion. We don't bother ourselves by catching the ball. But if the ball is in the reachable space, then we can catch the ball, and then we return it to the original motion. And the vision system will be estimating the ball parameters, like the center of the ball and its position in 3D space. And then it also needs to calculate the catch position. And if this position can be calculated, then they need to determine the trajectory modification. And in this case, we must be able to predict the position of the hand and the position of the ball. So the trajectory of the ball and the center positions of the gripper should be able to converge. If they don't intersect, then we go back and estimate the ball position. And if they can converge, then we take it to the hand reachable position so that it will be able to catch the ball. And the catching method, we need to estimate the joint angles using the thread order polynomial system. And we need to figure out the initial positions of our robotic hand. And we also need to estimate the position of our gripper so that we'll be able to direct the gripper to the trajectory of the ball so that it will be able to catch. And this is done by calculating the joint angle rate so that we'll be able to control the speed. And this is determined from the velocity of the ball. And during catching, we need to start closing the fingers using the step reference, at least 10 milliseconds before the ball reaches the hand itself, so that it won't fall outside the hand. So if we start closing the fingers at least 10 milliseconds before catching, then we'll be able to catch the ball. So the blue region here is demonstrating the reachable region where the hand will be able to reach in this area. This is the space where the hand can be able to catch the ball if it's passing around each of these points. So this blue space is demonstrating the working area, and this red cross is showing the tossing, and the blue one is showing the first throw, and then this one is showing the second throw, and the circle which is on the highlighted regions here is showing the catch positions. This is the calculated catch positions. So if the trajectory is pointing us to this position, this is the position that we target so that we can control the hand to catch at this point. But if this is outside the working region, you can see at this point it is outside the working region. Like I explained in the previous slide, we don't bother ourselves with the catching, so we just stop the catching in that case. And to estimate this trajectory, we use these equations to estimate the ball's motion using recursive least squares method. And you can see from this graph that this red plot is the positions of the ball that we have calculated. And the blue line is showing the trajectory which has been estimated using the least square method. So you can see it's nicely fitting, it's estimating the ball's positions. So having these estimations from the RLS, we can simply estimate the positions where the ball will come and intersect with the hand, and then we can run the control method. And the estimation of the ball's trajectory is showing with these figures where the line is showing the predicted trajectory, and the blue one is the first throw, this other one is the toss, and then the other one is the second throw. But all of them, they're showing the estimated positions, with this one having some challenges with estimating the positions. But all of them can be estimated generally. But at some point, we realize that there are some errors that we can calculate from the estimated trajectory and the computed ball positions. And this is when the ball gets out of sight. And for this reason, we end up getting the wrong center of mass. And this causes these problems because we tend to lose the ball that we are tracking. And then it causes this problem. So this is a demonstration of the tracking and the estimation of the trajectory of the ball. So the blue line is showing the actual positions of the ball, and this brown line is indicating the estimated trajectory of the ball. And as demonstrated previously, this is how we are catching the ball. And you can see that the fingers are closing before the ball reaches the hand in order to process the catching nicely. Otherwise, we're gonna miss the ball. It will bounce at the hand and then it disappears. So in conclusion, we can say we managed to estimate the ball trajectories with stereo vision using the high-speed cameras. And we also managed to succeed in juggling the two balls in one hand. And in future, we intend to analyze the grasping of the ball during juggling and increase the success rate of the throwing. And also try to make some improvements to the controller so that it can work better than the previous achievement. Thank you very much for your listening.
Students from Prima, from the same group. So I'm just going to share the screen here. Okay, this is going to look a bit weird, but I'm just going to have to do it this way. And then, 1 second. Okay, can you guys see the full screen presentation now? Can you guys see the presentation? Anyone open the mic, please?
Yes, but I also can see part of your desktop, the browser, and the taskbar.
Okay. All right, I think that's the best we can do. Okay, we'll start with that, yeah. All right, so I hand it over to the students in Plymouth.
So, hello, I am Marc-Antoine. This is Ajinka and Ama. We will present you a different approach of to coach an object. So, it's a different approach because this is soft coach, and we try to do something cheaper and more passive, something maybe slower, but try to do the same task to coach a ball. Is it as efficient as what we've seen before? So Ajinka will present you the design.
Okay, so for this Koan, the objective was to basically make a design which is more human-like. So what we had to do was to design a hand which is flexible, a bit like our hands. What this helps us in doing is when we want to catch an object, the arm kind of bends along with the object, and it kind of absorbs the momentum. And also, because the gummy arm is passively compliant, we actually get a little absorption of momentum in the arm as well. So the entire arm actually bends down with the object, as you'll see in the videos later on. So this basically gives us more time to actually close the fingers and catch the object. The entire process requires less computational effort because the passive morphology of the hand can you play this video?
See if you can play it. Oh, yeah.
Yeah. So in this, we just connected two fingers and using tendons to actually actuate it. So this is how the arm works. So basically, it has like 14 degrees of freedom. So the thumb has 2, all the other fingers have 3, and it just uses 1 degree of actuation, and that's the motor which is mounted in the gummy arm. So yeah, that's it for the design, and this is how it looks after it's mounted on the gummy arm. So now we'll move on to the touch sensing, and Mark and Tom will present that.
So to be able to feel the ball arriving into the end, we decided to use a touch sensor. This is, as you can see, an Arduino Micro with a tax strip. This is 5 sensor in the same I2C in the same board, which is connected to the Arduino with I2C. So something really good with this touch sensor, this is I2C, so you can connect to the TagFast. This is the official I2C board, or to the Arduino, or if you want to any device you want. So So this touch sensor has a really big advantage. You can split each sensor to different parts to connect it to the board, which give you the ability to have a touch sensor on each finger. And you can extend it to 40 sensors, so much more than what we need. And another good thing is you can extend the area and you can feel the temperature into it and the touch sensor in the device. Currently, we are able to receive the data, but we need to implement it into the end to be completely, to feel exactly on each finger on when the ball is inside the hand. So now for.
Hello, I'm Amar, and I've been working on the algorithmic portion of soft catching. One of the central characteristics of the project was getting our inspiration from bio-inspired algorithms. That's why we have procured Microsoft Kinect, as human beings don't use more than 60 FPS per second in our eyes. That's why we have used 30 FPS, which kind of makes the estimation process quite slower, but it is bio-inspired. We have used OpenNI, PCL, and OpenCV for processing, and the methodologies used for object tracking are color-based reason growing, and the segmentation is being done based on the normal and the smoothness factor of the objects, and the constraint is basically the color. And the second approach is SSB color segmentation and pointer extraction, and after that the centroid and the center of mass of the object is calculated. And using the first two approaches, what we can do is we can actually capture object of specific colors, but using the third approach, that is correlation-based segmentation, with clustering in PCL, what we can do is the gummy arm could catch anything and detect trajectory of any particular object based on the change in the correlation between two frames. For trajectory estimation, as you can see in the figure, that is the points that have been calculated when the object was being thrown towards the gummy. As you can see, there is a slope in both the x, y, and the z coordinates, and those 6 points, they actually show the trajectory of the ball while it is being thrown. And you can see that the time span is from 8 to 8.5 seconds. That's why we're getting around 6 points, which is quite low for trajectory estimation. And the methodology that we've used for trajectory estimation is linear square regression. We haven't used any other estimation algorithms such as Kalman filter because as we said, we have quite low frame per second. And we have also explored kinematic modeling using projectile equations in all 3 dimensions and all 3 planes to estimate the coordinates. And for future work, what we're going to do is we're planning to estimate the workspace of gummy, and from the trajectory estimation, we're going to construct.
See in the video, it's recorded at 120 frames per second, and you're watching it like 4x slower. So you'll see that basically the arm kind of bends along with the object and absorbs the momentum, and it allows the palm time to close. Good to do that. So you can very clearly see that the deflection in the gummy arm is actually taking the momentum into it and allows the hand actually time to close. And that's quite a good height to start off with. So yeah. So thank you.
All right. Okay, so that's the end of the presentation, and we now.
In the gummy arm is actually taking the momentum into it and allows the hand actually time.
All right, everyone, make sure you mute your microphones if you're not speaking, and then the tutors can open their mics to ask questions to the groups.
Okay. May I ask first, or Tapio, would you like to go first? I don't know if you can hear me, guys.
Go ahead.
Okay. Well, first of all, I would like to congratulate both groups because, well, I really think these are 2 interesting works or 2 interesting approaches to solve kind of the same problem. Since I'm more into the computer vision part, that's where I'll focus my questions, if you allow me. And first of all, I would like to ask the first group presenting, Chiba University. So guys, are you there?
We are here.
Okay. Well, the way you detected the ball, it was simple, but at the same time, I think it was efficient. So congratulations because of that. But I have some questions. First of all, what is the frame rate of your cameras? Are those high speed or just 30 frames per second regular cameras?
A very high speed camera capable of capturing 1000 frames per second.
Okay. And what is your processing speed? I mean, because I saw that you're processing with CUDA in GPU. So what is the real frame rate of the system?
We set up to about 500 Hertz.
Good enough. Also, I was wondering that this is not only related to the computer vision task or part, but also to the grasping. How do you deal, or how do you handle false positives, false negatives? how that affect the catching or the trajectory estimation, if you have any. You know
Can
what
you
I
ask
mean?
the question?
Yes. Usually when you detect the ball, or I assume that when you detect the ball, you will have false positives sometimes, or perhaps false negatives. How does that affect the trajectory estimation?
That's the point where sometimes you end up having following the wrong trajectory. I saw the slide where you find the point where you are supposed to get the location of the ball, where you are getting the estimates, the trajectory that you are tracking. It goes to a different position, and then you lose sight of the ball. That's the problem that we experience. But if you set the parameters efficiently, then you can find the estimation problem easy to manipulate.
Good. Also, one thing that I missed from your presentation is a better demonstration video. I mean, one showing the whole scenario with the ball trajectory and the hand grasping it. You know what I mean? Instead of, well, because we just saw a short video of a close-up hand catching the ball instead of the whole trajectory and so on.
The whole trajectory of the ball, or
yeah.
the working space where the ball is throwing and then is catching.
Yeah, but maybe including a video of the whole thing would have been great.
Yeah.
But in any case, good job.
Okay.
Also, you introduced at the beginning the problem of juggling balls, but in the end, is your robot able to do that?
It can juggle 2 balls, but with 3 it's very difficult to manipulate that.
Okay. So from my side, that's all for you. Is the Plymouth group there? I guess so. Guys from Plymouth.
Hello, yeah.
Hello again.
So we're having some network problems. We're trying to connect up a Ethernet cable. Could you repeat the question?
Well, I was going to start because I was talking to Chiba before.
Okay, go ahead.
They did great. And I have just a couple of questions for you guys in the same sense as for the others. How robust is your ball detection system? I mean, at any point, is the error too big for the rest of the system calculate the trajectory of the grasping?
As we are using just 30 Hz for the trajectory calculation, that's why we don't have enough number of points. As with throwing of the ball actually is done in half a second, so we have around procured 9 points maximum from the throwing of the ball. So that kind of poses a problem. Our trajectory estimation isn't that perfect, but because it doesn't give you the exact position of.
Oh, I think I'm losing you again.
Try to minimize the error, and because
I'm so sorry. I lost you for like 10 or 15 seconds. Can you say that again?
Actually, as we have just got procuring 9 points out of our throwing of the ball trajectory, because we have only have using 30 Hz from QNet. So and we're also not using estimation filters such as Kalman, because that's going to take up a lot of computational time. So our trajectory estimation isn't that robust. There is an error of around 5 centimeters right now, but in the future works we are planning to reduce the error. But as GummyArm is compliant, so I think an error of around 3 centimeters or 2 centimeters is optimum for GummyArm to catch an object. We don't need a particular perfect estimation of the ball position.
Okay. And in your opinion, what would be the best way of adapting what you already have to more complex trajectories, such as the one we saw in Chiba, I mean, elliptical or that sort of thing?
The guys in Chiba, they're actually using quite highly sophisticated system. They're using 500 Hz tracking, trajectory tracking hardware, and but we are not doing that because our entire system is based on bio-inspired, so we are trying to condense all of the algorithms within around 50 hertz. So we have that constraint in our mind while we are working on the algorithms. So we cannot actually use more than 50 hertz. That's the level.
Okay, and just my last question. Maybe it's a stupid one, but I was thinking about what happened if you increase the weight of the ball. For instance, I mean, in your videos, you were trying with different distances, which of course has to do with the force with which the ball. So if you increase this weight, what would happen? What's the limit for the hand?
We didn't actually see what the limit is, but what we did observe was we had a smaller and heavier ball, but we were able to catch it because what happens is it basically, from the same height, it has more momentum. So the arm actually deflects more, but because it kind of absorbs the impact, it kind of vibrates about its position, but we can close the fingers quickly enough to actually be able to catch the ball. The limitation of the hand was actually the ball size, because if it gets too small, the arm was actually the hand was designed for catching objects greater than a particular size, like the red ball you see in the video. So if it gets smaller than that, the object actually slips out. That's the only limitation right now. So we were looking to improve the design, didn't have enough time to do that.
Good. Well, that's all for me. Good job for both teams. I really like it.
Okay, thank you, Jose Carlos. I think we can have one more quick question from our tutor, and then we have to switch groups. We're running out of time here. Tapio or Fabio? Hello.
I have a couple of really short questions. I was, first of all, wondering about the material in the hand for the gummy arm. Was it the Vitaflex 20? And then another question is, was the screaming sound in the video coming from the robot actuation?
Go ahead.
Okay, so the arm was kind of modeled upon the Open Bionics anthropomorphic arm. So the fingers which you see, they're made up of silicon, and to provide rigidity, we attach segments of 3D printed plastic to it, and those segments actually serve another purpose. Though they allow us to route tendons through them. So that is the actuation mechanism for our fingers. And as for the screaming sound, that was the servo, because when you actually hear it in slow motion, the frequency changes and it sounds like it's screaming. So nobody was hurt in the demonstration.
Okay, thank you.
Okay, I think we'll have to leave it at that. So let's give.
Martin.
Oh, Fabio, go ahead. Go ahead. I can hear you.
A quick question for both groups. Is for Chiba, but also for Plymouth. To what extent you think that having a soft end helps you in the catch? This is what impacts have on the algorithm, the fact that you have a soft end to catch the ball instead of a rigid one. This is a question for both groups, for Chiba and for Plymouth. Not necessarily in the work that you did already, but in principle or in future implementations. Did you get the question?
Yeah,
yes,
I got it.
Yes. In Chiba, we may think that it will depend on the design of the gripper with the soft catch, but it will improve the catching capability and the control of. You see, in our system, we need to control the fingers at least 10 milliseconds before the ball reaches the hand itself. And I think if we can manage to get the soft catch, we can control the catching capabilities as soon as the ball reaches the hand itself, not before the ball reaches some space before reaching the gripper. So I think if we can have the soft catch with very accurate sensors, we can be able to incorporate them that at the point of contact, it must start closing the focus.
I see.
Okay.
And Plymouth?
Yeah. Yeah, if you want to.
From the demonstrations that we've done, you can see that it gives us more time to close the gripper. So it compensates for the hardware limitations that you have, such as slow camera, and even if the position is not estimated correctly, if the hand is slightly badly designed, for example, it just manages to compensate for that, the passive compliance. So I think it's a promising design. If you could maybe just improve some of the specs, like maybe a slightly faster camera, 60 frames a second maybe, and maybe a better gripper. But the time that it gives us to close, I think that's the biggest input that the passive design gives us.
No, it's a general comment is that merging the two approaches may help a lot. Although probably you would have to just a minute. I just arrived in the lab. Would probably help on both sides. You should probably change the structure of the algorithm. So, and here I'm where also Anna Julia is. So no more questions. Okay, thank you.
Thank you. Let's give them a big applause. Okay, so we're running behind schedule, no problem. I suggest the speakers that spoke now, if they could disconnect, just so we have enough spots for the next group, or we probably already have enough. You can watch these presentations on the live stream on YouTube, and then we get ready for the next group. So if you guys can make room for the people coming in. So wherever you want, sit here if you want. Yeah. Oh, in there. That's fine. Yeah. So okay. So group 3 and 12, get ready. We'll take 2 minutes to get ready here, and then we. Okay, so do we have, is Andy there as well?
Yeah.
Okay, great. All right,
Yeah.
cool. Are you guys ready as well?
Yes, we're ready. Everything here.
All right, so welcome back everybody. So we'll now have group 3 and 12, Guans 3 and 12 presenting. And we'll start here in Plymouth, so I'll share the screen from here. I have with me here Beatrice and Christopher. So let's start sharing. I should do this first. Pro, this one. It's going to look a bit weird, and then we'll play from start. Okay, can you guys see the full screen presentation? Someone open the mic and say yes or no?
Yes.
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 Okay, thank you guys. All right, so go ahead.
Thank you, Martin. So good morning. My name is Beatrice. I'm sitting at Plymouth University with Christopher Woolbridge, and in Humboldt University there is Andreas Gerken and Benjamin Barth, who's we've been working together in Koan 3, basically. We joined Koan 3 and 12 because Koan 3 seems like the logical step before Koan 12. Koan 3 is, the scope of Koan 3 is exploring gates with a quadruped model from Zurich University, published in 2004 by Rolf and Ida. It's a cheap model that can be 3D printed, so basically we took it, and it's a nice platform for going on towards Koan 12, which is gate categorization. So we built 3 platforms, one in Humboldt, 2 in Plymouth University, and today we're going to go through the construction, the coding of each of the platforms, and how we explore the gates in different terrains and different. The 3 platforms have also differences between themselves, and then some on sensors data. So we called it names. We call them Hans, Alice, and Bart. So to differentiate them, so Hans is sitting in Humboldt, and he has one single power supply of 7.4 volts with a step-down converter for not to burn the servos. So we have to basically power the controller, is an Arduino board, and the servos. So then we have Bart, who's sitting in Plymouth University. He has some ultrasonic sensors to not hit objects in the range, and the batteries are feeding the servos for AA battery that can be improved, and then we're feeding the Arduino with a different battery or with the serial cable. It's not a lot of power that it needs. So the 3 of them share the same structure, the same model. Bart and Hans went for the rigid spine, where the Alice has the flexible spine, which has some compliance on it.
Okay, can everyone close their mics, please? Can everyone close their mics? Thank you.
So in Alice we have the flexible spine from the design from Zurich, and some rubber from the feet, and touch sensors in the feet as well. So now I pass it on to Andreas, who's going to talk about the construction.
So, hi from Berlin.
Oh, you can say more. Oh, sorry, my bad. 1 second. 1 second, yeah. Whoa.
That's good.
That's a bit. Yeah, there we go. And there we go. Yep, go ahead.
So I will talk a bit about the construction. For example, we in Berlin. Why should we read robots? So it's all about the synthetic methodology. So we have the robot behave in a real environment as it does because it's an embodied agent. It really has to behave in the real environment, and if we have a simulation, it will always lack of detail, and it's easy to cheat by leaving something away, and it will completely change the behavior of the robot. And even if we would have a good simulation, in the end we would have to test the program which we evolved or programmed on a real robot to see if it works in the real world. So about the construction in Berlin, We started without knowledge of 3D printers and without knowledge of the puppy platform itself. And the goal was in total to see how much effort it takes to get into the 3D printing process and how long it takes to build a puppy. And in the end, to compare the different versions of the puppies. So we have a Ultimaker 2 printer here in Berlin. So it's fairly a good resolution. And we have a workshop with many parts, which was very helpful during the building process, since we didn't have to buy all those screws. So for the effort, it took from a time and financial perspective to print all the parts, which you can see on the right. It took, summarized, accumulated, I think about 14 hours to print and to print the parts and remove the support structures. And I thought it would cost a lot more than the result showed. But we calculated that it costs around 1 to 2 euros to print the whole body. So here we can see calculation of all the costs for the robot. So in total it was 140 euros. And the biggest expense was the servos, the actuators, and the smallest expense was just the body. So in total, we think, we didn't calculate it, but we approximated 40 hours to write a program. So you can see some building process here. And in the middle picture, you can see that we didn't know about support structure and how to configure the program in the beginning. So the results were pretty bad in the beginning, but we managed to figure out how to do it. So this is the result, which you can also see here in real time with some circuitry on top. So, and in the next step, we're going to talk about design principles, which are taken from the How the Body Shapes the Way We Think book, which we read. So, first about the 3 constituent principle. We think we fulfilled the principle, since we always looked at the body and the task and the environmental niche, which was in the beginning the laboratory carpet, but we will later see too that we put it in another environmental niche on the playground in the real world to see how it behaves there. So about the complete agent principle, we always tested the whole body of the agent and not only the legs, for example. So we fulfilled that. We have cheap design, since we exploited the environment through passive actuators. So we have springs. So we didn't need sophisticated actuators through exploiting the environment. We have partly a redundant system, since when one actuator fails, the system can still behave in a different behavior, but it can still move, maybe. About the sensors, Beatrice will say something about this later. But we don't have redundant sensors at the moment, but it's planned to build them in. So we have in the future touch sensors and IMUs fused in one agent, so one can fail. About the sensory motor coordination, BART has at the moment ultrasonic sensor, and it can stop when it approaches a wall. But about the real sensory motor coordination, where the complexity, where the structural stimulation is induced by the sensory input, this is not done at the moment, but planned. About the ecological balance, all 3 parts of the agent are balanced in a way. So sensors, motors, and brain are equal from the complexity. As Christopher will say later, we have ROS running on some agents. So you could say that that's a parallel, loosely coupled process. And about the value principle, it has self-organization through morphology and self-stabilization, which is some kind of value, but it doesn't have value-driven behavior. So it's also partly maybe better for the future. So that's it from Berlin. I'm giving to Chris.
Okay, thank you. So I need to share again here. 1 second. Okay. Sorry for the psychedelic effects. Okay, can you hear us now?
Yes.
Yes.
Okay, cool. We can go ahead.
Right, so yeah, I'm going to talk a little bit about the coding that I designed initially for BART. We did try it on Alice a bit later, but I'll talk about that in a second. So the code structure, so we've got the Arduino boards on the puppies. I made a custom servo library to allow us to easily adjust all the parameters for the different servos. For BART, it checks the ultrasonic sensor and then drives the servos. I then have on a laptop a little HTML website that then connects to the puppy using ROS serial client protocol, which allows me to change the parameters of his walking gait online. So there's the interface that I made. So I've gone into a few different parameters. So the speed is actually degrees per update cycle of the Arduino. I wanted to do a little more with the control, but actually all the control does at the moment is allows you to turn on and off the servos. So you can have just 1 or 2 servos running at a time. Then you have the minimum position in degrees for the servo and the maximum position, allowing you to adjust the stride length. And the offset, which allows you to delay the starting of one of the servos so that you can get a nice variation in different parts of the legs. So, with that said, I'm going to show you a little bit of our gait experimentation, if we can open up the YouTube video.
They are in my presentation in this moment.
Can I click on them?
You can go. Yeah, you can go here.
Okay.
Just play it.
Okay.
Yeah. Because it's
all right. So this is the initial calibration. This is how we set it up. We've got a treadmill. We've got a safety line there, and the USB cable is how we're actually connecting. We did try and get Bluetooth working, but it's a little difficult. So some of the gates didn't work so well. We call this one the bucking your shirt, and as well as falling on his face, he does a kind of donkey kick every now and then. So here we're moving on to some of the better gates. I call this one the giraffe gait because it's moving left legs, then right legs. This is actually the default parameters when you open up the site, but it works quite nicely, I think. This is a trotting gait. It's moving a little faster, as you can see, but it's a little unstable. He tends to wander around the place a little. We're having to use the safety line quite a lot to keep him facing the right direction. And then this is actually one of the best gaits. This is the bounding gait, which is what we thought would probably be the best. This is actually the fastest BART moves at. This is also after a little tuning towards him. So we then loaded the same code onto Alice. So this is them doing the giraffe gait. In this case, Alice actually performs the giraffe gait a bit better than BART does. But the trotting gait, Alice is possibly even more unstable in terms of direction than BART is, as you see, moving around the place and almost turning 90 degrees at points. The bounding gait, BART was a little better, but at this point he's as I said, these parameters at the time were tuned, so we're just loading the same parameters onto Alice, and it's you can see her legs slipping a little. And so we have the And then I thought I'd put in because every movie needs an after the credits bit. This is actually the Berlin robot, but this is actually quite a good video because it shows him walking through the sand, which I think is pretty impressive. And is one of the main objectives was to take him out for a walk. So unfortunately, here in Plymouth, the weather's been too awful for us to take our robots outside, so it would have blown away.
You would have short-circuited.
Yeah, the rain.
I keep going.
Yeah. And I'll hand us back to Beatrice now, who's going to talk a little bit more about Alice and her senses.
Yeah. So sorry. So those were videos of gates tuned for Bart. So what happens if then we tune them for Alice? It performs a lot better. Like there, we can see the spine actually taking some of the force of the moment and then allowing the back legs to impulse. Then the trot gait, like tuned for Alice, we can see here, is quite interesting because it starts turning, but then at the end it self-stabilizes somehow. So it's quite amazing what you can do with the body, because here we're just sending a constant sine wave of positions to the servos. So now it just goes straight. And then, so it can even climb steps without knowing what it's doing, just like going forward. So it's quite a nice platform to try and close the loop with the sensors data and see. So there it is. It did it. So we have 4 touch sensors in each of the legs. We're using ROS, as Chris said, ROS serial Arduino. Here is the platform at rest with the gallop gate, where the back and the forward legs have the same, only that the servos are in opposite directions. So we can see the touch sensors are receiving different pressures, so the center of mass is not perfectly aligned, as it happens, as we know, is in biological systems. So here is some raw data from the sensors. Like on the left, we have the gallop, and on the right, we have the trot. So it reflects how complex this data has not been filtered. We have to think about what we want to do with it, how we want to filter it. Do we want to filter it? Do we only want to look at the maximums of each point? And just like very simple data, or so it reflects how complex the world is. For such a simple gate, we're not modifying any input parameters. It's always the same, and yet. And it's a flat area as well. So a conclusion here, well, here is a small video of the platform without any controller, just with someone actuating, moving a potentiometer. So regulating the voltage signal to the servos, and only 2 servos on the back. And what it can actually do, that body, with some type of intelligence behind. So the body and the context matter. One gate in one body will not work in another if it's not tuned for it. Inputs are tuned for a given body. As complexity increases, we realize like Bart doesn't have like a flexible spine, doesn't have rubber feet. So it was a lot easier for us to just tune the parameters for it. Whether with Alice, I found it a lot more complex because the body starts having more complexity. So, for example, the trot gate we saw in Alice that walks quite nicely in the RoboCap field. It falls in its bum when it's walking in a different carpet with different patterns. So, yeah, the context is evident to us now that the context really matters. So future work is really moving towards Goan 12. First, we would like to integrate the best designs elements in each of the platforms. For example, the power subsystem of hands, or the touch sensors of Alice. We would like to integrate some Bluetooth communication, an IMU sensor to look at the accelerations, and to align in a certain direction. So really, Coan 12, a nice first step could be to use the platforms to design a control system that recognizes when a gate is good and adapts the gate to changes in terrain or in the context. Then test new legs that they design in Humboldt. You can see there the stress-strain analysis. And will the robots be able to develop a good gate in different terrains? So we built a repository where we are sharing our code and then thank you to Martin and Ricardo, our supervisors, and ShanghAI Lectures.
All right, thank you guys. Let's give these guys a round of applause. Okay, so let me stop presenting. All right, there we go. So, great presentation. We are open for questions from the tutors and anyone else that wants to ask questions. Anyone want to start? Do we have a question? Anyone? Ricardo, do you have a...
Hello?
Yeah, go ahead.
Let me break the ice. So, well, again, congratulations. That was a very interesting presentation. I just have one question that I don't know if it's very simple, but I'm pretty sure you will be able to answer it. It's just, well, I saw you have 3 designs. The 3 of them look very nice. These are variations from the original one. But my question is, can you extract any conclusion from the 3 designs and the test you have performed? Also, all of the challenges you have faced. I mean, you have rubber feet, flexible spine, no rubber feet. So is a more complex approach better, or as you were saying, that will depend in the final application? That will, of course, depend on how well tuned is the control. But in your opinion, if you had to make one for the real world, which one would you choose?
I think, personally, I would probably go for the more complex one using the flexible spine. Not sure about the rubber feet, to be honest, but say the flexible spine, I mean, that's going to help with getting over some obstacles. I mean, Bart, we've mostly been on treadmills, on carpet. He hasn't done much effort in the rough terrain, but I think the flexible spine certainly helps with the getting up the step kind of problem.
Yeah, that's the thing. Like the simpler design will work in a simple setup, but as the world becomes complex, you need to. I think you need to go for more non-linear design.
Any thoughts from Berlin?
Yeah, that I think that it's hard to say which one is the best just from our expectations. But when the robots can learn, maybe in the future, we will see what emerges from which body and which body behaves the best for evolution. So maybe it's not the part of the designer to see which body behaves the best, but evolution will figure it out. Maybe.
Okay, thank you. You convinced me. You have my 140 euros.
All right, we have more questions.
Just a comment. I think that Fumiya will be very happy to know what you did. Because this is a dramatic downsizing of the puppy. So in terms of cost, easy of design, it's so very cool. Nice.
Watching this presentation, I could see that this one had a lot of
things involved like material science, programming, mechanical engineering, electronics. What I would like to know is which one was your biggest challenge, you know? Looking everything like 3D printing, putting together the electronics, programming the Arduino, doing the experiments. Which thing was the most challenging one?
For me, it was putting together the hardware. I'm sure Martin will tell you, had many hours of amusement watching me drop screws as I tried to put the legs together. Excuse me.
For me, it was the communications, I guess, because yeah, you have to play with the rates. I still don't understand certain things why they work, and that was the biggest challenge. And the biggest surprise was the potential of the actual physical platform, which I did not expect because I worked with the model last year in the simulator, and it's a lot straightforward, like with the physical platform.
Any thoughts from Berlin?
So for me, the challenge was the programming. I think the group in Plymouth was much farther sophisticated in this category, but I think we can still manage it in the future.
And for me, the most not challenging but fun part was the building, since as programmer you normally just program stuff and don't build so much. And it was really fun to work with a 3D printer the first time.
All right, thank you.
Thank you very much.
Any more questions?
So I have another one, if nobody has a question. So for the next year, which kind of suggestions would you give to the people from outside that is thinking, oh, should I try the ShanghAI Lectures? Should I try a koan?
Yes, go for it.
Yeah, it's been very interesting.
Yes, I'm very applicable to the whole course, even though you feel like you have enough classes and coursework, and then it all integrates through. There is always some application in your classes. It adds value for me.
Yeah, I'd agree on that.
So as I had this before with robotics, and I saw how sophisticated the analytical solutions are, I think this is a very nice approach to really build robots that actually can behave in the real world, and was really interesting for me.
Yeah, I agree.
Okay, thank you very much.
All right, thank you guys. So we are a bit over time still. Is there a last question from anyone? Tapio, Jimmy, do you guys want to have any questions for the group?
No question from me. I arrived a bit late. I haven't heard the whole. Oh, sorry.
Sorry. Yeah, no worries, no worries. Okay, if there's no more questions, then I think we shall end it there. Let's give them another big round of applause. I think this was a really good work. Thank you. And with that, we'll have a little break again, and we shall have the next group coming up very soon. Let's keep
Bye.
Bye. All right, bye-bye. Thank you. All right, so do we have the presenters in Pisa ready? Just open your mic so I can hear you.
Yeah, but actually, in the same place.
Okay, yeah. Yeah, excellent. All right.
So cool. But was that your wife? The girl in Plymouth was your wife?
Yeah, that was my wife. Yeah. Yeah. Yes. Fabio, can you hear me? Okay, I can't hear you right now. All right. So yes, you guys are sharing the screen already. Fantastic. So I think with that, if everyone's ready, we'll start the last presentation for today. The last presentation for the ShanghAI Lectures 2015. This will be Group 5 presenting from Scuola Superiore Sant'Anna in Pisa. So guys, whenever you're ready, feel free to start.
Can you hear us?
Yes, we can. And we can see your slides. If you can try to go full screen, see if that works.
Non sento più nessuno.
Ah, perché dovete parlare voi.
Ecco perché. Ok, ma si vede? Okay, can you hear us?
Yes, we can. Can you try to put your presentation full screen, if possible?
It's full screen. It's already full screen in our
Okay, well, I think it looks okay like this. We can see the presentation okay, so I think you can start.
Okay. Perché non va?
C'è un po' di ritardo.
Okay, let's start. So good morning, everybody. We are 4 PhD students from the Biorobotics Institute of Scuola Superiore Sant'Anna, and we are presenting our project that is called A Soft Touch. Our idea was to combine a robot, an industrial one that you can see behind me, Romao alarm, with a soft gripper in order to demonstrate that it's possible to use soft materials combined with this kind of robot. What is soft robotics? Soft robotics is a part of robotics. I think that's some problem with the presentation.
Cosa farlo? Cioè, come funziona? Sto solo ritardo.
No. There's a little delay in the presentation. Okay. But you can see the slide, so I keep on.
All good.
What is soft robotics? Soft robotics is a part of robotics that started with the initial challenge that was, can we build robots with soft materials? And during these years, soft robotics followed a lot of application from the biomedical ones to manufacturing, to agriculture, to marine applications, using the characteristics of soft materials. So why soft robotics? Soft robotics can help to achieve adaptable and more safety and more efficient robot. So it's possible to apply this kind of soft materials and soft components to different application and use it for in different range. So, and soft robotics is going to stand as a novel approach to robotics and artificial intelligence, and it's not just a new direction, but the use of soft materials in robotics is going to snake its fundamentals.
Sorry, but the slides are not turning. I don't know why.
Yeah.
Maybe you could click on mirror show in your presentation, so that you see the same on both screens, and then we'll see it in full screen.
Come faccio a chiudere?
It was in PowerPoint, I think.
Adesso forse si fa. No.
Okay, so now we lost the screen sharing and the video. Could you try to screen share again? That's good, yeah. And now full screen. On your presentation, I think you see it.
Okay. Okay. And we started from the study of typology of grasps in human. We can have two kinds of grasps, the precision ones and the power ones. In the power grasp, we can have a low level and simple manipulation, but in precision grasp, we can handle more delicate objects. So a grasping robot can restrain objects or can manipulate objects. And the industrial robots with the industrial grippers are able to perform a specific task, but they are not so flexible and adaptable. So what is needed to control the motion? In a power grasp, we need to move the arm and the wrist, while in a precision grasp, we can move only the fingers. So, and the effector in industrial robots are able to do simple tasks and very task-oriented, and they show a high level of dexterity and capability in this kind of task, but they show also a low anthropomorphism and a low manipulation capability.
So, the objective of our study is to combine the soft manipulation with the dual arm. That is a rigid, big robot, two-arm robot. We used two Festo grippers that are rigid grippers, and we customized the grippers by inserting two add-on, three soft add-on, one in each finger. So we made a soft gripper that is able to grasp and manipulate objects, even delicate objects. So we improved the robustness and the adaptability of the grasp. And the task that we chose, the grasp, was to unpack a full shopping bag. So there was groceries on a table, like eggs, salads, tomatoes, and so on. And we picked one of each kind of objects, one time with one Festo gripper without the soft touch, and another time with the gripper with the soft touch. And then we could compare the two results of the manipulation and of the grasping. For this use, we used a dual arm command robot and the Festo gripper that were on the dual arm. The Festo gripper is a typical basic gripper that is not suited for manipulation and is not suited to manipulate delicate objects. And thanks to the soft add-on, we were able, in fact, to manipulate delicate objects like eggs without breaking them. The setup that we used was composed of three parts. One was the vision. We obtained the vision using a Kinect camera, version 1 of the Kinect camera, to identify the objects and identify the depth in the space. It was a 3D space. And then we used the Festo gripper that is on the photo, down on the right, but we used one without soft add-ons and another Festo gripper with soft add-ons. And then we used the Comao dual arm robot that is shown in the picture. Is composed of two arms with 6 degrees of freedom and another degree of freedom that enable the two arms to rotate respect to a central joint that is a torso joint, and this allows jaw movements. And the robot is cooperative.
Okay, hello. I think we lost you here for a moment. Can you still hear us? Can anyone hear me?
Yes.
Okay. All right. Guys in Pisa, I didn't hear the last thing you said. And the presentation has stopped moving. Fabio, can you hear me? Okay. So let's give them a couple of minutes to connect up again. They might have lost connection. Do let me know if any of you do hear them. We'll just give them a couple of minutes. Okay, Fabio, can you hear me? Fabio, can you hear me? Maybe turn on the volume. Fabio, hello.
Very nice, invece the 848.
Fabio,
Sorry, I lost the.
Okay, no problem.
So where was the last you saw?
Method.
Method. Okay.
Okay. In order to enrich our aims, and so having a soft touch, we designed the mold parts of our timbals in SolidWorks, and then we printed these parts in ABS, rigid plastics, by employing a rapid prototyping machine. Subsequently, we injected into the mold liquid silicone rubber in order to shape a soft timbals, the timbals in a soft stuff. And the overall results after several hours drying was this.
So we started with having the vision from the Kinect camera that was able to recognize the rectangle, and inside the rectangle the circle of the egg. So you can see the image. And at first we started with the Festo gripper as it was built first, and you can see that the egg was broken from it, since the gripper is very hard to deal with.
And then we made the other tests with the soft add-on put on the Festo gripper, and you can see that the egg was able to be manipulated without being damaged. We did more tests, of course, and only in one case we had the egg that was a little bit damaged from the finger, even with the add-on, but maybe the egg was not, it was fragile from its nature. And so you can see the difference between the two type of manipulation. We did the same test with the tomato to see how it was able to handle the object, and we did the same with the kiwi fruit, and we saw we had very good results since maybe the kiwi is even more has a more hard nature compared to the egg, so all the results were very successful. So we can conclude that the soft manipulation can be a really useful approach in robotics and in artificial intelligence. And through the help of the vision system, the soft grippers can actually increase the flexibility and robustness of a manipulation that is dexterous. Industrial robots, like the dual arm that we have here in Pisa, provided with soft grippers could lead to a new set of applications, which involves, as new, the manipulation of delicate objects. Soft material can allow us to obtain a more efficient grasp without actually having the necessity of having a high degree of force precision in terms of orientation and of the end effector and the contact surface. This was our results compared to the Festo gripper without the soft add-on. With the soft one, we were able to have a success of the grasping rate very high compared to the other one. And then we obtain an increased level of adhesion and adaptability to the objects due to the deformability of the material that is the rubber, and this was also possible. So this was the end, so thank you from the one number 5.
All right, thank you guys, very well done. Okay. So we are ready for questions from the panel. Just open your mics. I guess I could start off on this one. Thank you for a really nice presentation. I think it's really cool work. I was wondering, well, I have 2 questions. The first one's a quick one. I'm just wondering what, I didn't hear exactly what type of rubber you were using. So could you specify exactly what type of rubber it was? And then I was wondering, so you have here a system that has kind of a fixed type of softness in the finger. Do you think there are applications where by being able to vary this softness of the material could be interesting? For example, have some kind of inflatable membrane that you could pressurize more or less for different applications. Do you think that could be interesting?
Okay, the type of rubber was silicone.
Was GLS 40.
Okay.
So medium softness.
And actually, we are in our future works, we want to use the type of the universal gripper, in which we want to use a type of material that is granular, and by pressurizing, at the pressurizing, we want to change the stiffness of the grasping in order to be more or less soft. So we are developing it now, the interface to do that. And then in our first belief, we wanted even to do this kind. I share again the screen, so I show you. We wanted to use this kind of material that is still silicone. Okay, I wait for you to see the screen.
Yeah, we can see it.
You can see it, okay. So this one was still silicone, and it was adapted passive, in which we had even actuator in order to press and release in the grasping phase. So this can be another way to do that, even to apply actually already on the Festo grippers without changing the wrist that we have already in the dual arm.
All right, thank you very much.
Thank you.
Any other questions?
Yes. So First of all, thank you for the talk. It was very interesting. I like the idea of putting soft material into like the Festo grip. It helps, but so even if the gripper was more efficient to grab tomato, egg, or kiwi, where it is any downside in accuracy? Did sometimes the gripper miss the grab or grab the object in the wrong way?
Well, of course, from our experience, we see that with the Festo grippers without the add-on, the accuracy has to be very high in order to make the grasping very successful and have a high rate of success. With the silicone one, actually, it didn't even matter a lot the position of the egg compared to the three fingers, so we were able actually to have a good grasp without having a high accuracy. So maybe we thought it was even before because of the surface of the silicone was higher and was soft. So this was able for us to manipulate the egg and take it without damaging. With the other one, of course, we had to be more precise and in order to be able not to break it. Actually.
Thank you.
Any more questions?
One question here. You were talking about the vision algorithm to, I could not understand very well, to separate things. Which kind of algorithm are you using to find the objects? Or
Yes, we use the toolbox in MATLAB that is the computer vision. So we use the functions in MATLAB to identify rectangles and circles in an environment, and we use the different colors in the RGB camera to identify the table and the egg container and then the egg.
Okay, thank you very much. So is it a pure MATLAB toolbox?
Yes, yes. We interface the MATLAB with the alarm via TCP/IP connection. So with MATLAB, we are able to communicate with the Kinect, and then the Kinect gave us the position in the space, and we moved the robot in that position, commanding the Festo gripper.
Thank you very much.
Any more questions?
Yeah, I have a question. I was wondering how thick the rubber layer was in the contact point, and if the rubber was kind of giving in, kind of like the human skin. Kind of, if there's an object, it envelops itself around the object that takes the shape, or was it just not so visible softness, just friction that were
well, the rubber was not taking the shape of the egg. It was actually friction, and that's why we were able to grasp the egg easier compared to the other Festo ones. But it was not taking the shape in this first promising. We have only the difference between the front and the end of the finger. So here we have a different shape. So I don't know if you can see it. It's more curvy than the other one. You see that here is linear, and here it was. We tried to simulate I don't know, like a fingertip actually from here. That's why we thought it was a best way to grasp the egg.
Okay, thank you.
Thank you. Any more questions? Yeah, Ricardo, go ahead.
So besides the fingertips, was there any kind of softness within the robot? Because the robot looks quite scary to me from here.
For the moment, we had not very soft, but afterward we plan to make the two grippers that Anna Giulia said. So the universal gripper the one with the grains of coffee inside that can grasp any object, and the last slide that we showed that has an adaptive system with an underactuated mechanism and is very, very soft. And then we can implement an impedance control in the manipulator, so it can adapt like the mass spring system on the object to grasp. So this was for the moment we had the compliance of the figure.
Okay, thank you very much.
All right. I think that's all the questions I had as well. Jimmy, did you have a question?
Yeah, I have one more question. What do you think about the safety of your gripper? If you put your hand in the gripper and you close the hand, would it hurt?
Yeah, we used a low value of force to avoid these problems because the gripper is very strong. But with the use of these grippers, we didn't need so much level of force because the friction and the compliability of the fingertip was sufficient to grasp objects. So if you put your hand, it's okay. You didn't go.
What about heavier object? If you need to grasp a really heavy object with
heavier object, we need to do improvements on the gripper to avoid these problems. So we use the objects that were light and delicate.
Okay.
Okay, fantastic. Thank you, guys. So if there's no more questions, I think we'll thank the group again. You did a really good job, so another round of applause. Okay, so that's it, the last presentation for ShanghAI Lectures 2015. I think it's been really cool. We have a lot of good presentations over the last 2 weeks, including today. Any last thoughts from the tutors, Fabio? Students?
I want to thank everybody. Really, every year I think we are improving and building on the previous editions because, in particular today, but also the day before, all the works were extremely interesting. So this course seems a nice thing to propose because, as I told, I think last time already, we also see that giving trust to students is a good policy to get the best from the students.
Exactly.
I think that you agree with me, right?
Absolutely, yeah. And I think, yeah, I hope also we can, I think I'll ask all the groups, you guys in PISA, also the guys here in Plymouth and everyone, if you guys could, I think I'll set up a shared folder somewhere where you guys, if you can put maybe some videos, some images, and then we'll make kind of a compilation of all the presentations from this year, and we'll promote it on YouTube, on Twitter, etc., so we can get a bit of publicity about it. 'Cause I think there's a lot of cool stuff on here. And if you guys have open designs, like a link to your GitHub page or something like that, that would also be fantastic. So maybe I'll send an email about that later.
I fully agree.
Awesome.
Okay, so bye everybody.
Yeah, goodbye. Thank you for this.
Bye.
Bye, Jimmy. Jose Carlos, Tapio. Thank you. Appreciate it.
Bye-bye.
And hopefully see you next year.
See you next year.